Yeah, thanks. And I guess there's added motivation to stay on time because lunch is coming up soon. So let's all look forward to that. Yeah, so as the title suggests, I'll be talking about Majorana loop models in measurement-only quantum circuits. And since I think this subject is maybe rather different than what a lot of folks here work on, I'd like to start with a bit of background on random quantum circuits and measurement-induced phase transitions. So the basic setup here is that one, say, has a one-dimensional chain of qubits, and the dynamics that the system undergoes are generated by choosing at every position and time some random unitary, which could be Clifford or Haar random, and then as well some measurements, which could be, say, weak monitoring or actual full projective measurements. And now, because the measurements, of course, can, yeah. So Clifford is just the set of operators that map a Pauli operator onto a Pauli operator, and Haar is sort of a larger group of matrices that act on this. So if I'm just doing measurements, and even if I fix the positions and times, just averaging over the random outcomes, looking at the ensemble averaged density matrix for this system, what you'll see is that this just looks essentially like an infinite temperature state. But this is sort of a naive perspective on what's happening here, because we know in sort of an individual trajectory of the circuit, there's actually something interesting happening. Like, there are correlations. This isn't just this totally trivial state. And this is the central idea in this measurement-induced phase transition, that measurements can drive a transition, not necessarily at the ensemble level, but in the entanglement entropy at the level of individual circuit trajectories. So this is something sort of highly nonlinear in the state, and admittedly hard to access experimentally. And the sort of rough picture that one expects is that when measurements are dominating, they tend to sort of localize information in the system and destroy entanglements, so that you have some sort of area law phase at strong monitoring. Then if these random unitaries are to dominate, those tend to generate entanglement and spread correlations, scrambling the system, resulting in some volume law phase. And at this sort of transition between them, what you find is some emergent conformal symmetry at this critical point, and a log law entanglement scaling in your sort of typical trajectories. And so if we're just thinking about Clifford circuits, where all of your unitaries are just Clifford gates, say typically on 2 qubits, the sort of most generic scenario that people tend to see is that this transition is in the percolation universality class. I mean, of course, there are sort of fine-tuned examples where that's not true, but this very broadly seems to be the case. And just to give you a picture of why this is a good expectation, there's this notion of the minimal cut picture. So just imagine this circuit, and suppose that for each qubit we draw a world line. Then assume that every unitary, even though really they're random, let's just assume they're maximally entangling, sort of preparing a Bell state between the qubits they act on. And we'll take our projections to act, say, on a single qubit. And these will fully destroy the entanglement that qubit had previously had with the rest of the system. And what you essentially get now is this network where measurements are cutting these bonds and unitaries are giving you bonds. And the entanglement entropy, say, between 2 subsystems or of some subsystem A, just has to do with the minimal cut that you can draw through this network. So what that means is the path you can draw from this endpoint to this endpoint through this sort of space-time history of the circuit that crosses as few solid lines as possible. And the number of solid lines that it's crossing counts the amount of entanglement that crosses between, say, subsystem A and its complement. So this gives an upper bound on the entanglement that can happen, but it gives you a nice sort of picture for maybe why percolation should occur here, because it's just whether or not bonds are broken. Now, as the title suggested, this is not quite the scenario that I'm interested in. What I care about is actually measurement-only Clifford circuits. And this is maybe a more unconventional setup, because typically we think about phases and phase transitions as having to do with some unitary dynamics and competition therein. But here, I really want the entanglement dynamics to be generated exclusively by competition between measuring different flavors of Pauli operators that are sort of incommensurate with one another. And in this case, we don't necessarily have, say, volume law and area law. We can have topologically distinct area laws separated by some measurement-induced phase transition. And this is now maybe a bit more sensitive to the details of which operators we allow ourselves to measure. But that means we have maybe a broader family of possible transitions and phases. And sort of notably here, there are, of course, some very nice exactly solvable models, but because the space of possible circuits is so large, there's not really a unifying framework to really say, hand me a set of operators that I want to measure, and I tell you what kind of transition, if any, you should see in this circuit. So roughly, what I'd like to do here is tell you about some analytic framework for characterizing measurement-induced phase transitions in random Clifford circuits where the dynamics are exclusively generated by measurements. And then sort of taking that framework, I'd like to try to classify possible phases and transitions you can get in these systems and see if we can engineer sort of new entanglement phases. Cool. So I'll start off by talking about the sort of simplest possible type of circuit you can imagine, which is a free fermionic Clifford circuit. And here, the only allowed operations are essentially exchanges of Majoranas and parity measurements. And since this is measurement only, that's really what we want. What's very appealing about this is that because it's a stabilizer state and it's free fermionic, all of the information about your system is just encoded in the two-point functions of the sort of initial and final time fermionic operators. And so really, all you've got is just a circuit which can scramble and repair these Majoranas. So this admits a diagrammatic representation wherein, of course, a braid operation is just exchanging, but a projection operation is just connecting to sort of Majorana world lines.
Sorry, what initial states do you allow?
It just has to be a stabilizer state. Anything that's, I guess, like a pure state with
So
sort of...
Stabilizer in which basis?
So I guess you should just... Your initial state could either be maximally mixed, or you should have your initial state be given by a set of pairings between Majoranas so that there's some fixed value of the expectation of that parity. So as long as those are always like 0 plus or minus 1.
Which will be useful to assume for your talk?
Yeah, I mean, the initial state really doesn't matter because you just sort of feed in whatever here, and all of the physics happens in the actual bulk of the circuit that you run. So of course, you could imagine you put in something weird here. Maybe you can think of a fun example where that matters, but the actual details of the transition that should occur are in the circuit. And if you run your circuit for long enough, you eventually are going to erase any information about this initial state anyways, because of this randomness. Yeah. Okay. So what's maybe appealing about this, and I'll try to formalize this in just a moment, is that what was sort of formerly a totally random circuit, now you have a diagrammatic representation, and people have been thinking about the statistical mechanics of classical loop models for decades. So there's no shortage of literature that one can go back and refer to really try to dig into this. And one now has a direct dictionary from quantities that we might want to compute for these entanglement transitions to quantities in the loop model. So for example, the mutual information between two subsystems at the final time of this circuit just amounts to asking how many loops connect sort of subsystem A to subsystem B along the top boundary of this two-dimensional space-time that the loop model lives on. So yeah, this is the circuit in some sense that is run on some initial state. And similarly, if you're interested in asking how a maximally mixed initial state purifies under the circuit dynamics, That's a question of how much information from the initial time boundary remains sort of undestroyed at the final time. So it's counting the number of spanning loops. And really, all of this information is essentially encoded in the distribution of loop lengths for loops which have both endpoints on the boundaries. So the problem reduces quite a bit just to studying classical loop models. But maybe I can motivate this mapping a bit better by sort of quickly boring you with a little bit of operator algebra. So if I just look, say, at swaps and these projections on Majoranas, I can very quickly write down the operator algebra for this type of circuit. And I'd really just like to point out these last two, which are the important ones. This sort of first bit tells you that, OK, a projector squared is just itself. And in the diagrammatic representation, that tells me a closed loop can be removed and just replaced with a factor of 1. Or in the loop language, my loops have fugacity 1. And of course, this second relation is just telling me I can straighten out loops. There's ambient isotopy on these sort of loop diagrams. Now I should say this relation here is technically not true if you're just looking at the actual projectors themselves. There's a factor of 1/2 missing. And this comes from the fact that if I do this measurement once, I measure something that it anti-commutes with, then I measure it again, I'm throwing away half of those outcomes. But because I'm tracking a single trajectory, I'm always normalizing my state after each measurement, and so that factor of 1/2 just goes away. Good. And so, of course, if you walk down to some mathematician's office and ask them to give you some intuition about this system, they will do the exact opposite and just tell you that this is something like the degenerate Berman-Murakami-Wenzel algebra, and you'll have learned less than you'd set out to. But luckily, this actually simplifies even more. And that's because we care about entanglement. And entanglement is agnostic to the outcomes of the measurements, just cares where we did our measurements. And so this gives us an equivalence relation on circuits where the sort of sign of whether I sort of cross my loops over or under, it doesn't matter. So one can make this identification and simplify these relations a bit. And now the operator algebra has one name instead of 3. Now it's just Brouwer. And let's try to ask a little more about the structure of this algebra. Sort of a key aspect of this Brouwer algebra is this notion of orientability. This is a sort of hidden U1 symmetry that's maybe a bit unintuitive. The idea is as follows. Since every operator is quadratic in Majoranas, if we can partition our Majoranas into two sets A and B, then all of the world lines can be assigned a conserved orientation. So for example, here, if I just have nearest neighbor measurements, I can assign sort of odd and even sublattice Majoranas with an up and down arrow. And then every measurement I do will sort of consistently connect these in a way that doesn't bring two arrows together. But as soon as I introduce, say, some swaps, I see that I'm trying to connect loops that should have the same orientation, or that it's just no longer conserved there. So this is a U1 symmetry, but it's really the measurement analog of a time reversal symmetry. And this is super important as far as the sort of appropriate nonlinear sigma model goes for describing the system. So when you have orientability, the algebra, simplifies even more, but the nonlinear sigma model for your theory should be some CPN minus 1. If I break orientability, I go down now into RPN minus 1. And this has sort of massive impacts on the universality of the transitions that you can get in these systems. So to comment on this a little more, these equations should look hopefully familiar if you've spent any time in the 60s reading about Potts models. But I think none of us are quite that old, so let me just remind you, the Temperley-Lieb algebra, which bears almost an exact resemblance to this last line, is an algebraic description of ON loop models without crossings, or Q equals n squared state Potts models. And the nice thing is that it has this diagrammatic representation via loops where these generators are just measurements, essentially. And so just from identifying these algebras, you might naturally expect for nearest neighbor measurements, you should have, with loop fugacity 1, you should have a one-state Potts model, and that's percolation. Fugacity is just exactly this scalar factor. So it's to say if I do the same measurement twice in a row, in the loop picture, I have a closed loop. And I can remove that closed loop out of the diagram and replace it with some scalar factor. In this case, the scalar factor is 1. So it's just a weight that should show up in the partition function when you're doing a sum over all possible loop configurations. Okay. So just to expand on that a bit, with nearest neighbor operations, if I now also were to allow swaps, what I essentially have are things that look like this. When there's no swaps, I just told you that's the temporally Lieb algebra. It should be percolation. When I do have swaps, these loops are now allowed to cross over one another, and I break orientability. And what one finds is that whereas I have critical percolation here without swaps, when I break orientability, that percolation critical point fans out, and I have an extended Goldstone phase. And this transition now here is in a totally different universality class. And the Goldstone phase itself is a little funny because you get these logarithmic corrections to loop observables. And because there's this identification between loop observables and entanglement quantities in the circuit, that means that if I were to go implement a circuit that falls in this Goldstone phase, I'm going to see corrections to things like entanglement. So instead of log law entanglement at the percolation critical point, in the Goldstone phase, I have log L squared.
Sorry, maybe I missed it, but in Goldstone, what is your mode? What does you
It's an extremely unintuitive one. So
it's okay that it exists, yeah?
yes, yeah. So you can view it in some sense as the loop fugacity 1 is some replica limit of higher fugacity, or if you want to be really fancy, there's all this terrible supersymmetric theory stuff. But I think it's better to just say it's unintuitive, but it's there.
How I would measure it, or it would measure, but like how it would show itself, so to say.
Yeah, so it shows up in these corrections to the sort of correlation functions for the Majoranas or your statistics for the lengths of your loops. So that's exactly like if I look at the half-chain entanglement entropy, instead of log L scaling, I see the square of log L. Cool. Yeah, so this is known, and one expects this with swaps. But now the question is, can we sort of take this and get some intuition about the case where it's really measurement only? And sort of a useful tool when you're doing measurement only is this notion of a Majorana lattice representation. So suppose I take like a 1D chain and I just rearrange things to look like this two-leg ladder. Each node here is a Majorana and edges are some allowed type of measurement. And if this lattice is bipartite, then the loop model is orientable because that's exactly this bipartition that I need for orientability. So for this sort of way of drawing things, there's three very natural ways that you could choose some orientable subset. And in all of these cases, if I only measure these operators, I will never break this hidden U1. So exactly this example, if I say measure z, xy, and yx, what you essentially find is that when there's no z measurements, I have two decoupled critical chains. It's sort of a fine-tuned case. But as soon as I turn on these z measurements, that's really you can sort of look at this first picture here. I'm adding some interchain coupling. And as soon as I turn on that interchain coupling, I kill this critical point and I go into an area law phase. But what's rather funny here is that this area law phase has an exponentially large correlation length. So if you're doing some experiment and you have fewer than, say, 10,000 qubits, you're going to think it looks fairly critical. And you can even tune how critical it should look in some sense. The reason for this is that there's this terrible mess about network localization for models in class C, where it turns out that really, as soon as you couple two layers, say, of Chalker-Coddington networks, this splits your percolation critical point into two. And the way that we've set up this circuit, just turning on any finite z measurement, you're moving directly up. And the correlation length that you get in the system is exponential in the inverse pairing, basically. And so it takes really large systems to see that there actually was a gap opened up. Yeah.
First, you have 5 minutes.
Okay, sure.
Second, to do large system numerics, you must be assuming a Gaussian state.
Yeah. So that's the starting point.
That's
Yeah.
why it's all
Yeah.
tractable.
Yeah. Exactly. Yeah. So then, if I sort of break orientability by explicitly choosing operators that make this lattice non-bipartite, I see I do open up a Goldstone phase. It has sort of all of the appropriate signatures of universality of this loop model with crossing that I saw with swaps, but it's generated in an exclusively measurement-only scenario. So percolation and this CPLC Goldstone phase are really the two generic scenarios for free fermionic circuits. Now, I'll try to go quickly here and just maybe get the highlights. But for non-Gaussian circuits, it's a bit of a mess, right? We have Jordan-Wigner strings. We can break fermionic parity. But if I'm in a phase with area law entanglement and short loops, most of the time that I do a measurement, I know a lot of these local parities. And so measuring some really large operator always simplifies down to a very small quasi-local operator. And moreover, just from an RG analysis of Potts models, we should expect that higher order interactions should be irrelevant in a lot of these cases for one state. For parity breaking, you need to introduce an ancilla to sort of effectively restore this loop picture. But when I introduce this ancilla, the punchline is that the ancilla effectively mediates some non-local swap in the bulk, which can break orientability. And it turns out that then if I go look at some extremely generic Clifford circuit, say that only has 2 qubit Pauli measurements with just some operator A, B is measured with probability A times probability B, as soon as I break away from the free fermionic limit, I can open up this Goldstone phase. It has the same universality that we just saw before. And this really is not a fine-tuned case at all. So this Goldstone phase shows up in a massive family of measurement-only Clifford circuits. Yeah, I'll just give the highlight here. Another thing you can do is try to sort of explicitly couple Potts models through these, say, 4 fermion terms. And this is trying to align the loop configurations, say, in 2 copies. What we know from an RG perspective is that this type of coupling is irrelevant. So I have this massive region in the phase diagram where this coupling does nothing. But you can sort of write down this transfer matrix for this circuit and get a coarse-grained loop model where it turns out there's this strong coupling fixed point. You can solve exactly this phase diagram. And what you find is there's a BKT transition here, there's a percolation transition here, and there's this Ising tricritical point here. So it's the tricritical one-state Potts model, which is in the Ising universality. And essentially, the idea is you are taking sort of competing interactions which, under some duality mapping, take the system to a diluted Potts model. And so really, just by understanding the algebra of these projectors, you can try to engineer really unconventional transitions in these measurement-only circuits just by reading through old literature on how to couple Potts models. And probably, since I have very little time, I would just say if this is of interest, you should go look at the posting on arXiv. And just as sort of an outlook, there's still quite a bit left that one can think about here. So loop models can really have generic fugacity, and people have studied this for decades, and one gets quite a bit of exciting physics as you change the fugacity. So a nice question is, can we implement some adaptive circuit just using Clifford projectors and say some classical assistance to change the effective loop fugacity and thus the type of criticality we get. Similarly, loop models have this notion of dense and dilute phases, so we can try to use a classical assistance to flag these as active and inactive and implement an even broader class of loop models. And lastly, there's some recent ideas about doing one final layer of measurement which has different probability distribution. And what this essentially amounts to is, say, I had some 2D POTS model, and I changed just some parameters at the boundary, so we can try to look at surface transitions in POTS models just through these circuits. And this tells you a little bit also about the robustness of certain types of critical states against boundary perturbations. Yeah, so I guess there was a lot there, but the short and skinny of it is that you don't have to do any hard integrals to understand Clifford circuits. You can just draw pictures. And if you like drawing pictures, you can really engineer a lot of funky measurement-induced phase transitions that are really hard to see otherwise, just from guessing and checking quite a lot of operators. Yeah, so I guess I would refer you to the posting on arXiv if you'd like to see more, but otherwise, thank you.